Bismillahirrahmanirrahim. Dear students, welcome to ECA1 class. The contents of today's lecture is series parallel networks. Now, what is series parallel networks? A series parallel configuration is one that is found by a combination of series and parallel elements. For example, in this figure you will see that we have both series and parallel combination together. Now, from this figure, R3 and R4 are in series with each other, and this series combination is basically parallel with R2. Similarly, this R2 is in series with R1 after solving this whole configuration. So this is basically the series parallel network in which both series configuration and parallel configuration is present. Now let's see a general approach that how you can solve this series parallel configuration circuits. Take a moment to study the problem in total and make a brief mental sketch of the overall approach you plan to use. The result may be time and energy saving shortcut. Examine each region of the network independently before tying them together in series parallel combination. This usually simplifies the network and possibly reveal a direct approach towards obtaining one or more desired unknown. It also eliminates many of the errors that may result due to the lack of systematic approach. Redraw the network as often as possible when the reduced branches are undistributed unknown quantities to maintain clarity and provide the reduced network for the trip back to unknown quantities from the source. When you have a solution, check that it is reasonable by considering the magnitude of the energy source and the element in the network. If it does not seem reasonable, either solve the circuit using another approach or review your calculations. Let us consider an example to understand that how we can solve the series and parallel configuration together. In this example, we have to find all the current and voltages. Let us consider this circuit in which we have to find the current and voltages. We have to find IA, which is the current of this shaded region, IB, which is the current of this shaded region, and IC, that is the current of this shaded region. We have also find the value of I1, the current flowing through R1, and I2, the current flowing through the resistor R2. We have to find the voltages of this shaded region. It means we have to find the value of VA, VB, the voltage of this shaded region, and VC, the voltage of this shaded region. In the first step, we simplify this circuit by solving the series and parallel configuration. Now from this figure you can see that this R1 and R2 are in parallel, so we can solve this circuit using a parallel configuration. Now this shaded region, you can see that R4 and R5 are in parallel, and after solving this parallel circuit, it is with series with the resistor R3, and R6 is basically the resistance of RC. So when we solve it and we get that equivalent circuit, so RA is basically the parallel combination of R1 and R2, RB is basically the parallel combination of R4, R5 and with series combination of R3, and RC is basically equal to R6. Now we have to find the values of RA, RB and RC. So you will see that from the figure RA is equal to R1 parallel to R2, R1 parallel to R2 using special case relation for the two parallel resistor R1, which we study that RT is equal to R1 into R2 divided by R1 plus R2. So substituting the values of these, we will get the value of RA, which is equal to 3.6 ohms. Now taking this second shaded region, so we will find the value of RB. So RB is basically equal to R3 plus parallel combination of this R4 and R5. So here we also use the relation of two parallel resistors R1 into R2 divided by R1 plus R2 plus with series combination R3. So when we substitute the values of R3 into and R4 and R5, we will get the value of this shaded resistance of this shaded region, which is equal to 6 ohms. Now RC, which is the resistance of this shaded region, is equal to R6, which is equal to 3 ohms, because it contains only a one resistor. So the equivalent in the equivalent circuit, we find RA, RB and RC. Now find the value of total resistance of this whole circuit. Now from figure you will see that RB is parallel with RC, and this parallel configuration is in series with RA. So we can write that RT is equal to RA plus RB parallel to RC. So using the relation of two parallel resistors, R1 into R2 divided by R1 plus R2, and add it with RA, because RA is in series with this parallel configuration. So after substituting the value, we will get the value of RT, which is equal to 5.6 ohms. Now we have to find the value of IS, the source current. You have the value of E and RT. So using Ohm's law, we can find the value of IS, which is equal to E by RT. Substituting the value of E and RT results in IS, which is equal to 3 ampere. So the total current of the circuit is 3 ampere. Now from figure you will see that this IS is flowing through this shaded region whose current is IA. So we can write that IS is basically equal to IA, which is equal to 3 ampere. Now when this current reaches this point, it splits into two parts, IB and IC. So using current divider rule, we can find the value of IB, which is equal to RC. Current divider rule states that when you are finding the value of the current through RB, it is equal to the opposite current, which is opposite resistance, which is equal to RC into the total current, which is equal to IA, divided by total resistance of the circuit. This is basically the circuit where the current is divided. So the total resistance of this circuit is RB plus RC. Substituting the values, we will get the value of IB, which is equal to 1 ampere. Now you have the value of IA, which is equal to 3 ampere. You have the value of IB, which is equal to 1 ampere. So now you can easily find the value of IC using Kirchhoff Current Law Kcl. Kcl states that the current entering the node is equal to current leaving the node. Here on this node, IA is entering, IB and IC is leaving. So when we apply the KCL to this node, we will find the value of IC, which is equal to IA minus IB. So substituting the values, the value of IA is 3 ampere and IB is 1 ampere. So the value of IC is basically equals to 2 ampere. Now we have the value of IS, IA, IB and IC. In the next step, we are going to find the value of VA, VB and VC. So in this step, if we are going to find the value of VA using Ohm law, VA is equal to IA into RA. Substituting the value, we get 10.8 volts. Now VB and VC are in parallel. It means that the voltage of VB is basically equal to VC. So we can write that VB is equal to IB into RB, which is equal to VC, which is equal to IC into RC. Substituting the value, we will get the value 6 volts. Now if you add these two voltages, you will get the total voltage. It means the result is correct. Now in the second step, we have to find the value of I1 and I2 also. So when the current is entering this point, it splits into two parts, I1 and I2. Now here you can apply the current divider rule to get the value of I1 and I2. First we find the value of I1. I1 is equal to, I1 is basically current flowing through resistor 1. So applying current divider rule, the current divider rule states that when you are finding I1, use the opposite resistor R2 multiplied by the total current entering the node, which is IA, and the total resistance of this network, which is R2 plus R1. Substituting the values, we will get the value of I1, which is equal to 1.2 amperes. Now again apply current divider rule to get the value of I2R. You can use KCL at this point to find out the value of I2. So we applying the KCL at this node. KCL states that current entering the node is equal to current leaving the node. Here current entering the node is IA and leaving the node is I1 and I2. So when we apply KCL to this point, we will get I2 is equal to IA minus I1. Substituting the value, IA is equal to 3 ampere and I1 is equal to 1.2, which we calculate here. So the value of I2 is equal to 1.8 ampere. So we find all the values of the current mentioned in the circuit and the voltages mentioned in the circuit. So this is the solution of this series and parallel configuration. You can solve any question related to this configuration using this method. So that's all for today's lecture. If you have any question, you can write in comment box. Thank you very much.